Okay. Last ones here. Okay, on behalf of ETSAP, I want to welcome you to this afternoon's webinar where we will, Mr. Juan will navigate us through how we can use times models to look at near optimal solutions. That's not only looking at least cost solutions. This webinar is a part of the advanced training project of ETSAP. Yeah, and today Juan will guide us through a presentation and he will open up for questions during the presentation. And we hope that we can have a dialogue and some discussions throughout the session. And we will also have some time at the end for more open questions and discussions. So please, Juan, the floor is yours.
Thanks, Neil. Hi, everyone. Nice to see or to read some familiar names here. Today, we will discuss about how to explore near optimal solutions or the near optimal solution space in times models. I think it's important to start saying that this isn't something that has been or was implemented almost 10 years ago. So it's a functionality of the framework that has been somehow forgotten or not used that much. At least in my experience, working with times model for the last 6 years, it's something that we are just using more and more because it's triggered by discussions with stakeholders outside the energy system models community. Well, today I will cover quickly or briefly the concepts of near optimal. Then I will explain a little bit the times features that can help us to explore this. And I will show you some applications, some ideas that I prepared using a model that was created. So it's based on a model that I created to test these functionalities. Unfortunately, the demo models were not suited for that. So I created this one. It will be also available, I think, on the website together with the slides. So you can also test it, and I'm open afterwards or available afterwards for questions and discussions if you are interested in that. So there are like two main takeaways that I want you to have from this presentation. The first one is that exploring the near optimal solution, then the term exploring, it's very important. So you need to find how to do it. And we will a little bit touch upon this. There are methodologies to go outside then optimal solution, or this idea that the optimal solution is the only one and the true solution. This is relevant today because in the past there was uncertainty, but I think that today there is higher uncertainty. The world is changing quickly, rapidly. There are policies, there are more discussions. 3 years ago, the policy-oriented discussion was different than today. Now we have tariffs, for instance, and trade wars and so on. Geopolitically speaking, it's also more unstable than 30 years ago, 20 years ago, when projecting the next 10, 5 years was a little bit much easier. And because of all of this interaction, there are more stakeholders. So before it was the energy system models were dedicated, used, and developed for and by energy experts. But now more people outside our field are checking the results, are discussing on the news, on some organizations, NGOs, and so on, how to reach those climate targets, what will be the impact on society, what will be the impact on labor, nature, and so on. So exploring outside the near optimal cost technique or least cost optimal solution based on technologies, it's important, but it's not the only part of this discussion. So in times, we can explore these near optimal solutions. There are some limitations, of course, I will explain, but I want you to be aware that is something that can be done, like recent models or energy models, frameworks like PIPESA or Calliope, and so on. They also offer this optionality to explore the near optimal space. They have some methodologies, for instance, the sport. I will briefly explain about that for PIPSA. So it's something that is like a very interesting when you talk about this with non-modelers. So for us, also in the team, we had modelers that in the past didn't know that we can also do it. So they were somehow challenged by the interaction with other models, but now knowing that we can do it has opened a door of opportunity for us in the discussion and to increase the credibility of the model and the results. So a little bit of the theory, just the picture there is like a nice introduction. So we have this global optimal or optimum point. That's the highest peak in the mountain range, but there are like several mountains that are also interesting and feasible, and from different points of view and for different stakeholders might be the best solution. That's what we want to explore. So this, like the traditional explanation of the near optimal is that you find what is the optimal solution from the cost minimization perspective, and you deviate from that. So you open up the space. We call this like increasing the tolerance by a factor epsilon that can deviate. So that's the additional cost, additional budget that you are giving to a model to find another solution. You might find that there are like different configurations, substantial configurations, for instance, different capacity, different operationals with the same capacity, and so on, because there are a lot of points that remain hidden in that. Before, another way to explore this is with the traditional parametric techniques, heuristic techniques. So we find parameters in the model that we change, and we find different results. That's basically what I believe you are also doing in your teams. So you define storylines, scenarios, you run those, then you compare them, and then you see if the future will go towards this direction. This will be the cost optimal solution. However, this might be challenged by stakeholders, and that's our experience at VITO in discussions with industry, with utilities, with infrastructure providers. They pursue a different agenda, and they see the evolution of the energy system in a different way. So we need to acknowledge that there are real world constraints and situations that are difficult or are not modeled at all. So the model is reaching for that cost optimal solution without taking this into account. So parameterizing those is very challenging. So we need to open up the catalog of opportunities and options for the discussion with the stakeholders. In the traditional parametric one, this is an extreme case, what you are seeing on the right. So you change some attributes, and then you have a higher cost investment or a higher operational cost. In my experience, at least in the model of Belgium, in times VE, in several runs, you don't deviate that much. So it's always less than 1% the deviation. Substantial different results, like different capacities, but it's very close to that optimal cost or budget. So the model will find a way to really stay around that optimal. So now we need to force the model to go farther and to explore other options. So the mathematical formulation is like you start from the traditional minimization of the system cost, but you will increase the budget. Now you will optimize, and this is more or less like what we will do with times. So you will change the objective function, could be minimizing or maximizing a user constraint. That user constraint, it's a direction that will take us far from that optimal point. So the inside approach, that's the one that we can explore in times for the moment. So you start from the optimal, you find what's the solution space or the solution envelope. And the drawback is that you need to define what's the direction that you want to explore. For instance, it could be increasing the capacity of a technology that is not going to the maximum in that optimal situation. For instance, something that was very trendy in the like 4 years ago was hydrogen. Now models are showing that it's not the silver bullet, but you want to push the model to see what are the limits if you increase the consumption of hydrogen, or if you increase the production of local production with electrolyzers, for instance. That will be a direction. And that's one of the limitations of the approach, because you need to find and define the limitation. So the nice part, you can do it from expertise and experience, but also in the discussions with the stakeholders. They want to see probably what the market it's more or less indicating, or what's their gut feeling. So you can also explore what will be the maximum and lower level of that direction within the envelope. The outside approximation, it's very interesting. It's linked to an algorithm that is called Oracle, and it's a systematic way to explore the solution space. I will explain a bit about that methodology, because we don't have it yet in times. Yeah, I think that's another way to see the results. It's very interesting. I haven't seen it, or I haven't tested it in my model, but you can have the optimal solution and could be a surface, meaning that you have more or less or exactly the same system cost with different or slightly different operations. So a way that you can test this is that you change, you introduce a tiny change in your model, and you see if there is a difference in the objective function. So that will mean that it's still sensitive to those changes. 1% increase in capex of a certain technology, and so on. So we will explore systematically the near optimal space or solution space. Why? Because there are conflicting priorities. Again, from our experience, like industry, government, they also have models that are like pointing to different solutions. So that's when you want to contrast your results with theirs and what it would take to align them in terms of cost. So if we include a budget or an epsilon, that will be the additional cost, 1%. We are speaking about billions of euros, which is a lot of money, but 1% might be under the uncertainty for a long future. So that increase is worth exploring. This discussion, I think it's also important, will increase the confidence on your model insights for the ones that are using the model, but also for the ones that are like using the results of the model. And the other 2 bullet points, something that I also included in the slides, is that you can test the boundaries of the model. So you can see under which conditions the model heavily relies on one technology, and even by pushing to a different direction, that technology sticks. Might be wind for some countries, might be CCS, might be electrification of the fleet, and so on. So you will also identify what are like these like not regret options, but also what are like the vulnerability of the model to rely heavily on that technology, because it is in all the results. And also you can test what are like the inconsistencies in your model. So you can expect certain technologies to be used based on electricity or hydrogen and so on. So you push the limits of the model comes out with strange or weird results. So you can identify if you lack one decarbonization option in one sector, if something is not working correctly as it's supposed to be in the model itself. I think it's important to mention that you also hear it. There are like the ways to call this are like model to generate alternatives, and that's like a family of different approaches or methodologies. At the end, there are like, it's broader, I would say. So the model to generate alternatives is the one that you explore different directions. So you change the objective function. We will see it in a minute. And so on. Another way is that you can also have a multi-objective function. So you optimize or you change the objective function and complement it, like minimizing the cost, but at the same time you have part of the equation or part of the objective function is maximizing one technology. So you need to give a weight to those, and that's the challenging part of the multi-objective function. And then Oracle is a systematically approach. So it explores those distances that are interesting, and it converges. And that's the nice part of this methodology. And the spores, which is mentioned in PIPSA, they also have a weight. So they build a different equation or user constraint to minimize the dependency on some technologies in some regions. And they do it interactively, and they find different solutions. If you have questions at this moment before I show you how to do it in times, if not, I might continue. Okay.
Does anyone have any questions about the motivation and methodology part? Okay, then you continue, Juan.
Yeah, I continue. Then to show you how we can implement it, I think that we can complement times code with an external way to implement more advanced features. At some point, it would be interesting to include it if that's worth it. So we have the model to generate alternatives, but together with the Pareto frontier. And the Pareto frontier is like similar to the marginal abatement curve, cost curve that you see. So it's a trade-off between reaching a decarbonization level and the CO2 price that you want to pay for that. But you can complement this with the solution space envelope, and you will have like more points to explore. The problem with this is you also only explore the corners. So there is a lot of information that is hidden, and you need to define the corners. Then we move to the Oracle. In the Oracle, we have an option that you start from what you see there as a green triangle. That's the solution that you know. And the blue triangle is what is possible within the conditions. And then it starts to find the farthest points and try to converge the two. Once you converge the two, you can explore the corners, similar to the MGA, but you can also use methods to sample within the space. And I think that that's also interesting, because it could be that just by going to the corners, you are 1% higher, 5% higher than the objective function or the cost. But it could be that one of the other points is very interesting. I don't know you, but maybe you also have the same impression that you run the model several times with different storylines and you find results that are quite comparable. So there is no diversity. And then it's when the diversity tree comes into the picture, which I think is a very nice name. And that's another approach. It's not coming from the energy world. What they found is that you can change a lot of or find a lot of points in the solution space, but they are very similar. So you need to add another metric that is the diversity of those results. And then it will sample those points that are very diverse. So this is to complement the picture that if we explore the solution space, we should have different options. No, like just different colors of blue, but you have different colors, blue, red, green, and so on. So I think that that's important. It came from a train scheduling algorithm, and they found that basically the model was providing 10 times the same results using the same trains, the same scale. So they wanted to add diversity, because if something happens or goes wrong with one train, they should be able to have a plan B and C. So very interesting. If you are interested in that part, check it out. I think it's recommended for what we do to add diversity to the discussion, if there is any. This is implemented in times, like as I mentioned before, it was developed 10 years ago. It's not something that I developed. I'm just implementing it and trying to present it again. So we will face on the two-phase or trade-off analysis and the multi-analysis. The same explanation. So you have the minimization of the standard objective function in the model. You can change it by a user constraint. So we'll change the objective function, and you can run it again to make economic sense of the results. For instance, electricity prices is it's like the shadow price is how the objective function will deviate if you change the level of the constraint. So you need to link it to the economic value again. So we ran it like the last time. It's also recommended in the documentation as a standard problem. So you will find prices that are meaningful. So now in practice, how it's implemented. So I divided in 5 topics. So the multi-phase, the multi-objective, basically the stakeholder perspective is also a multi-phase. And to test the model limits is what I mentioned. That's basically the first and the second step of the multi-phase without running the economic sense. And advanced options to consider, basically what I have been mentioning so far. So I created a model that is 5 regions. It runs up to 2050. It's 24 time slices, 4 days, 4 hours. It includes all the sectors. Those are based on random data that I found out on the websites and so on. And for industry, for a project that is called AIDRES that we were involved in, that includes all the decarbonization options for the hard to abate. So I extracted those. So you need to activate in order to run in a stochastic way the model. So it's not a stochastic as you will include like a function of probability, but it's because it's built on the states of the world. So you need to run in different stages. So you need to activate this. So the everything boils down to this multi-phase table. So it's quite flexible as a lot of tables in times. So you can do a lot of things with it. The first table, basically you activate that you will work in stages. So you will have like 3 different states of the world. That's more or less the first row. And then it says that in the first state of the world, you will run with the standard objective function, which is, wait, let me see if I can activate my, yeah. So it's basically this one, the objective function, the standard one that we use. In the second state of the world, the model will run with the user-defined constraint. Minimizing that by default is minimizing, so you can play with a negative or a -1 to trick it and to have like to maximize one variable. And then the model runs again the objective function, the standard one. The other 2 or the last 2 rows tell the model that in the second state of the world, used the result of the objective function of the state of the world, the first one, and add a 2% of epsilon or deviation from that value. Then, well, this one we will see it in the multi-objective function, but it's basically the weight. So it multiplies the objective function that you have here. So you can build it with 3, 4, 5, several of the different user constraints to build this multi-objective that has to be minimized. And then in the final one, yeah, you say that for the next step, because it's for the next step, so take the state of the world result, and you can also add like a slack to deviate from that result if you want. But yeah, in general, if you want to see the max or the minimum, you have 0. So it has to be that value. Basically, this number, or well, the result of the state of the world 2 becomes the right-hand side part of the equation that is used for the next step. I built here minimizing CCS, for instance, so not to have that strong dependency on storage of carbon. So probably you are also familiar with user constraints, so you can be as creative as you want with them. Of course, there are some limitations, but they are quite flexible with what you can do. So in the model that I created, you can also test different ones. For the sake of time, I will just focus on like reducing the CO2, minimizing the CO2 for this moment. So same as I showed before. So you have like the objective function, and within the 2% difference or increase in the budget or in the CO2 or in the objective function, you want to find how we can go further in CO2 reduction. For this run, I don't have a hard constraint for reduction. It's just driven by the CO2 price. So that's why this makes sense. I think I will take the opportunity to now mention that in general, sometimes you need to pay attention to some assumptions or the design of the scenarios that you are using this one that are not conflicting. So if you are minimizing CCS, for instance, and you have a constraint on the same storage for that specific run, might be conflicting. And of course, or on the one hand, the model is unfeasible, or on the other hand, you have weird results. So you need to check that. So if I run that, for instance, the objective function or the objective function will be 2% higher. But I wanted to show you like in terms of CO2. So the reference and the state of the world 1 are basically the same. So it reaches like a cumulative sum of 53,000 million tons of CO2. If I increase 2% the budget or the breaking function for this one within the envelope and looking for that direction, it will go down to 20, more or less. So I think that that's very, very interesting to explore. And of course, like you can see how the cost is changing. So you will pay more, more for the cost act in this case, for instance, that investment is also higher. So everything becomes more expensive. But you are not paying that much more for the CO2 tax. That was like what is here. We will see this, that comparing the cost is very interesting when you have a trade-off between who should bear a cost. That's a discussion that we had in the past in Belgium, like residential sector, that was the case, is paying a lot for the energy transition. So is there a way that we can make things a little bit easier for them? Yeah, we can check here a lot of results. So where is the energy coming from? Which technologies are used to reach that higher level of decarbonization within the 2% of difference? Yeah, like in this case, it's like expensive import molecules, for instance, will solve a lot of problems without investing. That triggers a question like, we will have a global economy that can provide or supply in a steady state those molecules and so on. Before like giving you the opportunity to ask questions, because I think it's interesting to have a conversation, I will explain that in the GAMS files and also in the LST files, you can see this behavior. So first, like in the LST, you see that in the model basically runs 3 times. So you will see that the objective function, as I explained before, that's the standard one. So it runs. Then in a second step, it runs with the objective function that we defined here. And that's why these numbers in the table are important. But it has like the result of the first step as a constraint times. Well, it multiplies both sides. That's the thing, but the model will try to be cheaper, but it's forced to go to the limit. So it uses like, this is the 2% higher objective function based on the results of the first one. And then in the third one, you take the results of what it's like minimizing in this case, CO2, for example, and it will be the hard constraint on the third step. Yeah, I wanted to ask you if you have questions. Someone has questions?
I assume you open up for questions on how it can be implemented in VEDA, right?
Yeah, indeed.
Yeah. Or is everything clear?
Yeah, I think like you might be thinking how to implement it in your own model, which is fine. And that's why I also at the beginning mentioned that you can contact me afterwards. I have here examples of what I thought was interesting based on our discussions. Yes, James.
Hi, Juan. Just a very, very basic question, I think. Can you go back one slide to where or maybe 2 more slides where you had the VEDA tables?
Yeah.
This one, yeah. So when you're running this, are you just literally creating a new scenario file with these two tables in it, and you're running an additional case with it? That's all you're doing?
That's all you need.
Wow. Okay. Thank you.
Yep, you're welcome. Yes, Leo? Gareth?
Hi. Yeah, I just wanted a little bit more clarity about specifically these VITO tables. Why exactly for the state of the world 1 is there both that the attribute SUCOB for both obj1 and obj-z? Why is that listed twice with the same?
Since like the multiphase is based or is taking advantage of what was developed for the stochastic part of the model, so it uses this attribute. So it's linked to activating the stochastic run, and it builds like in the I would say in the stochastic, it gives like this objective set. The one is just to say to the model that it will run in multiphase mode. So it needs to be there, and then you see like this is set by standard, but the one is just to tell Vera to run the multiphase.
So you're telling it run multiphase, and the first state of the world solve for the minimum cost by saying that
for the standard
line.
Yep.
Right. I'm sorry. What the second one is? What's the difference between a stage and then a state of the world?
Where's Rem?
So one of your columns is called stage, and then the second column is state of the world. What exactly is a stage in this context? If a state of the world is a sort of a run optimizing on one thing or another.
Yeah. It's like it's still confusing for me. But in the documentation, the stage and the state of the world are totally different things. So basically, it's more or less how the algorithm goes, but the stage of the world is like one possible stage of the world. It's linked to more the stochastic part of how you can build.
Okay. Thanks.
Yep. Yes, Karen.
Hi, Juan. Thanks for giving an overview. In this particular scenario, you mentioned the 2% deviation from the original objective, that is the state of the world 1. So if you have a 2%, whatever the percentage tolerance we provide, you may find many solutions, correct? So so do we get all the solutions, or how the algorithm pick up one solution, for example? Depends upon the sensitivity of the model. But if even in my model, even providing a 0.001% tolerance, they are very close solutions. So how many solutions I can get? Can I decide that how many solutions to generate, or how can I control this one? That okay, I need 5 solutions, giving an additional 2% or 1%, whatever the model is doing.
Yeah, maybe I will split my answer in 3 moments. Like one, defining the percentage is quite challenging. That's also on the literature. So basically what they do is they have extremes like 1, 5, and 10. So 10 is too high for me in general. Like it's very difficult to discuss that with the stakeholders. You are true. Like if I go from 0.5 and 1%, basically the model is more or less the same. So that's why I mentioned that the diversity tree is a nice approach, and maybe something that we can borrow for the energy system, because we will try to find diverse solutions. But to find different options, you need to define different or combine different directions to explore. If I can go some slides back, quite a lot. Yeah, here. So the problem, as I mentioned at the beginning, is to define which direction to explore. So it could be that in my example is minimizing the CO2. That's one corner, but the other one is maximizing PV penetration. That's another corner, and those are 2 different direct solutions, but they are still within the 1 or 2% difference. So to define or to create different solutions is based on which directions are you exploring. The problem is like you are somehow limited to what comes to your mind to explore. which is why the Oracle explores those directions for you or defines automatically those directions. But the way to build different scenarios or to different solutions will be to define and combine those directions or variables. With directions, I mean the user constraint. So here, like I just minimized here, CO2 or maximize CO2 reduction, but you can build a user constraint as you want, and you can do it one by one. Sorry, jumping between slides, but this will help me a lot. So you can have the multi-phase. Basically, you run the standard solution, you run state of the world 2, and then what I did in my example, I rerun them all. But actually, you can define based on the 2% of envelope, find a solution where I minimize CO2 emissions, where I maximize solar penetration, and where I maximize hydrogen local production. Those will be like 2, 3, and 4. Those will become the right-hand side of that equation that you will run at the end in stage N. So you will build a solution that is a combination of all of these directions or corners that were explored, that lands in a different corner of the solution space. But I hope it's clear. Yes.
Yeah, I should explore. I should implement and explore a little bit more. Thanks.
Yep. Yes, James.
Sorry, Juan, just one clarification coming back to our colleague from I think the UK. On the different stages that you just mentioned there in the stochastic tree, and then looking at the table that you have here. So for your stochastic user constraint that you have NOpt CO2 max is right below where your cursor is, and then you have state of the world 2. Can you just have list like multiple user constraints in one file like this that you're then optimizing with different stages or states of the world, or like, are they stages or are they states of the world, or does it really matter?
Yeah, I think like the stage is just stay, because if you see it's only one, so that doesn't matter. So you basically stay there in stage 1. It's like a way to activate the stochastic part in times in VITA, and let's say to stay in that part of the branch, and then you play with the state of the world, and then you combine them.
Okay.
I think that's would be my explanation. I'm not an expert because I didn't use that much of the stages, but with the state of the worlds, you can have several constraints in one file, and you can combine them in each state of the world or each step independently, or you can combine them in one. So if I jump or I skip all of this part, this is also examples that will be on the slides. So how results from the model from other things. But what I wanted to go, so we go to the multi-object function, and that's where you combine two different user constraints. So one example is to have the standard object function, and then you add another part to that equation that has to be minimized. The problem is to define the weight. To give you, I took as an example emissions, system cost. The order of magnitude difference between the two is huge. So I opted for this example to multiply the emissions by the ratio between the money and the emissions. So basically, that will be like in my model, 22,000. That's the weight. But you can change that user constraint and say maximize renewables. And then you have a weight for wind, a weight for PV, and a weight for all type of renewables. And then you have a different user constraint that is similar to what Pipesa is doing. So they have a weight that is basically the random model, and they defined a weight that is how much installed capacity was used out of the maximum potential. They use that weight to build a user constraint that has all of the capacities of all of the regions that you are using in that model, and then you minimized the dependency. So basically, it will try to deviate from that region where you have a lot of dependency. So you installed all the capacity, and then you start like finding different solutions, actually changing the dependency, because it could be that if you run pipes or a European mall at this moment, it will put all the wind in the North Sea and build the connections and so on, but you don't want to see a mall because it might be very complicated to maintain and to operate and so on. So you want more diversification. So that's what they do in pipes. So you can also do it here.
Cool. Thanks, Juan. One other final thing, and then I'll stop. It'd be really interesting to see minimize costs, minimize CO2, and minimize something like residential electricity prices, like really finding the corner of kind of socially acceptable solutions.
Yeah, the prices, I think, will be very difficult because that's part of the dual. I don't know if there is a way to do it, to limit it, to have a mall that electricity prices or marginal prices cannot go up a certain level. I think it could be done to find a way around it, but I haven't explored that, or I haven't thought about it. So yeah, maybe to continue, like in the multi-objective, you need to define the outweight, and that's the challenging part. But I think it's important. Like this is the normal trade-off: cost and emissions. But if you have a model that has the climate model, so you can also minimize the impact on climate and so on, you name it. So I think it's more relevant when you combine things that are comparable. So capacity of certain conditions, certain technologies from renewables, for instance. So it's not a model. For instance, I have seen that you have a model that uses all of the wind and then uses PV afterwards. So if you want something that is deployed like in a more balanced way, you can use this approach. Maybe the stakeholder perspective is another application. I mean, like the discussion that I had was that, yeah, a lot of people complain that there's a study for Belgium and Flanders especially, that let's say half of the people cannot pay for what is the energy transition. So renovating a house, buying an EV, a charger, PV, and more expensive products. So it will be a lot of challenges for them. So what will be the way to minimize their burden? That's what I wanted to explore here. So you can also use the cost. So I use here the investment cost for them, for the residential sector, within here very extreme 10% higher objective function. So the model will try to minimize the cost of those technologies. Then you see that there is like a 46% reduction for the residential sector. The results here from this model, I think it's important to mention, they are not to be used or comparable. It's like a very random model, but it serves the purpose to show that you can use these features and how to use it. Then you see that in the state of the world, the model invests in cheaper but less efficient technologies. And then other sectors are paying for the transition to reach like a certain decarbonization level. For countries, like in Belgium, we have 3 regions. Usually like the model that I use the most is just 1 region. We also use the one with 3 regions for other purposes. But you have a European model, or you have a country that is like bigger than Belgium, with regions and economic differences between the regions and so on. So you can also reduce the cost burden on one specific region. That's something that I wanted to test to show here. So you have more or less the same logic as the residential, but then you build the user constraint just for the region 5 in this case. So it will show you that there is like a trade-off, even though that here is smaller, but then region 3 will pay more. And I based this on different criteria. So you can do it like by population, by economic, or the GDP. For instance, the power purchase parity, and so on. Sorry if you hear a noise, there is a evacuation siren here. They are testing, so I don't need to leave. So I built this on a distributed effort among the regions. So it's another user constraint that you can build. And you can see that there is some changes in cost for the regions that should pay the less. So that's bringing me to the final part, and I will open up the door for discussions, and then we can wrap up. To test the boundaries. So basically, if you stick to stage of the world 1 and 2, so you can go unlimited, let's say. So you don't impose 2% deviation, for instance, but I just want to see what's the maximum hydrogen or the maximum electricity that my model can consume in the final energy consumption. And this is to test the limits of the model, like discussions with people that are more inclined to see hydrogen demand being created in the coming years. So we can identify in our model, the maximum that the model can handle is this from final consumption, or including transformation sector. So still depends on how you define the user constraint. So basically, it is the same, but as you see, you can only use state of the world 1. So you just change the objective function completely. You don't need the first one because you don't need to have a point of reference. Just need to see what's the maximum or minimum that your model can handle of a specific technology or a specific commodity flow. So for instance, I wanted to see what are the minimum CO2 or the minimum maximum carbon capture without thinking if it's stored or used. What's the maximum that can be captured? So I think it's very interesting because it tests the limits and I would say how healthy the model is to answer those questions. Like you might have blind spots saying that we include that technology, it's never selected and so on, but might be that even in this case that you are testing to consume max hydrogen, the technology is not used, and it could be there is something wrong in how it was modeled that might need some correction, or silly things like you have a typo or something in the commodity and so on. So something that might be triggering that the technology is not used, or you can identify this is, for instance, like the minimum CO2 that the model can reach. So it can't reach 0. So it doesn't have CCS, for instance, because then you can create negative emissions as much as possible. So you also need to pay attention to those limits. Basically, you can argue that this is linked to the process emissions. Actually, it is to process emissions. So, or some technologies that doesn't have a decarbonization option. So that's what I wanted to show you as well. So we can identify that there is a sector, subsector, without a decarbonization option. In this case, in this model that I created, it was international transport or transport and aviation. Maybe again, like if you want to increase the consumption of certain commodity, might be that you need to change the limit time. By default, in some cases it's fixed, but might be that you need to change it because the model is unfeasible and so on. Sorry for the noise again. Of course, like if I increase or push the limits of the model for electrification, the results will be meaningless, but it will show you that, for instance, we don't have electricity consumption in one specific sector in industry that you might know because of other projects or other discussions that it has an electrification option. So it's another way to identify if we are lacking some of the alternatives in the model. We did it for hydrogen as well. So you will see what is used. A lot is used in the power sector as well to increase it. And I will leave you like you can do the same for CCS also and so on. And the advanced topics, I think like this is very interesting. I think that we can combine it with some scripts, Python scripts or something, and for the moment to see how these two can converge. That will be for me the systematically way to explore. But nevertheless, comparing the MGA or the heuristic and the oracle method, you will have some blind spots. So with the MGA, you define the directions, so the parameters that you want to explore. The oracles offers automatic way to explore those directions. But in general, both focus on the corners. So you need to find samples in that solution space. There are different methods that are mentioned for that are not implemented, as far as I know, in energy system models, but there are methods to sample within the space, not the corners, but within the space. And but there will be always unexplored areas. So I think that that's important. Like we just explore, but we don't cover fully the solution space. But I think it's worth exploring what could be different solution, especially to add actual alternatives to decision makers. And I think that's my last slide, Neil.
Thank you. I think you deserve an applause. But thank you very much. And we open up the floor for questions and discussions. And we will share these slides, right?
Yep.
So you can look at them also when you are working on your own. But then any questions or comments? What are the approaches people in this webinar would like to test with near-optimal or multi-objective optimization? Yeah. James?
For me, I'm interested in using it as a diagnostic tool to, as Juan mentioned, find the kind of technology limitations on whatever you've allowed your model to do to, do quality control of the model as much as anything else. For new models, especially.
We started to use this tool here after the advanced training and before Christmas. And we saw a lot of weak spots in our model after using it. Yeah. And you will explore it, I guess, Juan, further this year, and we're looking forward to see implementation of it, maybe in an ETSAP workshop at some point.
Yeah, we will continue, also learning
here
in our site. Just to finish, thanks all. But here is my email also on the slides. If you want to contact me afterwards, I will be available and happy to discuss.
Yeah. We are very happy that you took the time to present this methodology to us with hands-on examples, Juan. And I thank everyone for participating. And we will end the meeting now.
Yep. Perfect.
Thank you.
Thanks all. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye.